Imagine you're a cosmic detective. For centuries, your main goal has been to find the ultimate set of rules that governs everything, a complete, objective description of the universe. This is the grand ambition of physics, to write the story of reality from a viewpoint that exists outside of it all, a view from nowhere. You want to know what the universe is doing when nobody is looking. But what if, when you finally develop the tools to take that ultimate detached look, you found nothing? Not a void of empty space, but a void of information itself. This is the astonishing and deeply unsettling situation a group of brilliant physicists found themselves in recently. A discovery made today, November 26, 2025, that shakes the very foundation of our quest for knowledge. They weren't trying to erase the universe, of course. Their journey began with one of the most mysterious objects in the cosmos, the black hole. These cosmic monsters are laboratories for extreme physics, where gravity is so strong that it bends space, time, and all our intuitions. Over the past few years, scientists have made incredible breakthroughs in understanding what happens to information that falls into a black hole. They developed powerful new mathematical ideas, a kind of quantum toolkit that seemed to solve long-standing puzzles about these gravitational prisons. Flush with success, they decided to aim this powerful new lens not at a single object within the universe, but at the whole darn thing. What they expected to see was a picture of our universe in all its glorious complexity, described in the fundamental language of quantum mechanics. They were hoping to find the mathematical structure that allows for galaxies, stars, planets, and us. Instead, the math stared back with a blank expression. The calculations, derived from the most advanced principles of quantum gravity, returned a shocking result. A universe like ours, when viewed as a complete, closed system with no outside observer, would be utterly simple. It would exist in only one possible state. It would contain zero information. The vibrant, sprawling cosmos we see would, from this ultimate perspective, be a featureless, static point. This conclusion was so counterintuitive, so contrary to everything we observed, that it was immediately labeled a paradox. How could our universe, which contains enough information to fill libraries vaster than galaxies, be fundamentally empty? It's like opening the world's biggest book, only to find it has a single unwritten page. The answer, it seems, might be as strange as the problem itself. It suggests that the complexity, the richness, and the very story of the cosmos might not exist without a storyteller, or at least an audience. The universe, it seems, might need us, or someone like us, just to be interesting. To understand this cosmic conundrum, we have to rewind a little back to the year 2019. Physicists were grappling with the famous black hole information paradox. The puzzle was simple to state but fiendishly difficult to solve. When something falls into a black hole, is the information it contains destroyed forever? Quantum mechanics says information can never be truly lost, but Einstein's theory of gravity suggested black holes were one-way trips to oblivion. It was a heavyweight title fight between the two pillars of modern physics. A team of physicists, including the legendary Juan Maldazzina, developed a new mathematical tool, charmingly called the island formula, to referee this fight. This island formula was a triumph of theoretical physics. It was born from an even deeper idea called the holographic principle, which suggests that a volume of space, like the inside of a black hole, can be completely described by information living on its boundary, like a three-dimensional image projected from a two-dimensional surface. Using this formula, physicists were finally able to show how information could escape a black hole. It wasn't destroyed. It was intricately encoded in the radiation the black hole slowly emits over eons. The island formula worked. It solved the paradox and gave physicists a newfound confidence in their tools for tackling the combined mysteries of quantum mechanics and gravity, quantum gravity. Feeling emboldened, they decided to scale up their ambition. If this mathematical recipe worked so well for a black hole, a self-contained object within the universe, why not apply it to the entire universe itself? After all, our universe might be a closed system. Unlike a teacup or a galaxy, it doesn't have an outside. It doesn't have an edge or a boundary you can point to. If you travel in one direction long enough, you might just end up back where you started. From a certain point of view, the whole cosmos is one vast, self-contained entity. Much like a black hole is a self-contained region of space-time. It was a logical, if audacious, next step. So, physicists like Maldacena, along with others like Henry Maxfield and Donald Merrill, who studied simplified baby universes, began applying the logic of the island formula to a closed cosmos. They were essentially treating the universe as a giant black hole with no outside. They ran the numbers, expecting to see a mathematical framework that could hold all the complexity we see around us, the countless stars, the swirling galaxies, the intricate dance of life. But the recipe that had worked so perfectly for black holes produced a cosmic disaster when applied to the whole menu. The result was stark, simple, and utterly wrong. The result that emerged from the calculations was, to put it mildly, a shock. The mathematics indicated that a closed universe, viewed from this ultimate objective standpoint, has what's called a one-dimensional Hilbert space. That sounds technical, but the concept behind it is surprisingly simple. Imagine a light switch. It has two possible states, on or off. The space of its possible states has two dimensions. Now imagine a dimmer switch. It might have 100 possible states between fully off and fully on. Its Hilbert space is 100-dimensional. The universe we live in, with its trillions of galaxies, each with billions of stars, and every atom capable of being in countless positions, should have a Hilbert space of almost unimaginable size. Instead, the calculations screamed that the Hilbert space of our universe is one-dimensional. This means the universe has only one possible state. Just one. Not on or off. Not bright or dim, just is. There are no alternatives, no other configurations it could possibly be in. If there is only one possible state, then there is no change, no dynamism, and no information. Information, at its core, is about the difference between possibilities. The answer to a yes or no question contains one bit of information because there are two possible outcomes. A universe with only one state has no questions to ask and no answers to give. It is a story with only one word, repeated for eternity. This was a devastating conclusion for physicists. It created a paradox of cosmic proportions. We look out at the night sky and see a universe teeming with complexity and variety. We see nebulae painting the void with breathtaking colors, galaxies spinning in majestic spirals, and planets orbiting their stars in a cosmic ballet. Our own existence is a testament to this complexity. The human brain alone is one of the most information-rich structures we know of. All of this, every star, every planet, every thought, is a manifestation of the universe being in a particular, incredibly intricate state, chosen from a near-infinite menu of other possibilities. So how could the fundamental theory predict that none of this is possible? How could our most sophisticated understanding of reality declare that the universe is a featureless monolith? It was as if a biologist, after decades of studying the rainforest, concluded that the only life form that could exist is a single motionless rock. The observation of our vibrant reality and the prediction of a static, informationless void were in complete and total opposition. Something was terribly wrong. The beautiful mathematical tools that had unlocked the secrets of black holes had, when turned on the cosmos itself, shown a picture that was not just wrong but absurdly, fundamentally wrong. To truly grasp why this one-state universe is so shocking, we need to talk about what information really means to a physicist. It's not just about words in a book or data on a computer. In physics, information is the very stuff of reality. It's the answer to every possible yes or no question you could ask about the universe. Is there an atom at this specific location? Yes or no? Is this particle spinning up or down? Yes or no? The complete set of answers to all these questions defines the state of the universe. The more possible answers there are, the more information the universe contains. It's the ultimate cosmic database. Think of it like building a character in a video game. You have choices to make. Is your character a warrior or a mage? That's one bit of information. Do they have red hair, brown hair, or blue hair? That's more information, more choices. The vast number of possible combinations allows for a huge variety of unique characters. The universe is like that, but on an infinitely grander scale. Every particle can be in different places, have different energies, and interact in different ways. The number of possible arrangements, the number of possible universes, is what gives our own reality its texture and substance. Our universe is just one character sheet, filled out from a staggering number of options. A universe with only one possible state, as suggested by the paradox, is a character creation screen with no options. There is only one pre-made character, and you can't change a single thing about it. In such a universe, there are no questions to ask because the answer is always the same. Is there an atom here? The answer is immutably fixed. Is the universe expanding? The answer is part of that one single static state. There's no information because there's no distinction between what is and what could be. Without the possibility of being different, the concept of information becomes meaningless. This is why physicists were so horrified. The result didn't just say the universe was simple. It said the universe was fundamentally incapable of containing the complexity we see. Our existence itself is a paradox. Every observation we make, every scientific measurement we take, is an act of gathering information, of distinguishing one state of affairs from another. The very act of doing science presumes that there are things to discover, questions with answers that are not known in advance. The paradox, however, suggested that from a God's eye view, there is nothing to discover. The book of the universe has but one page, one word, one letter. When a theory gives you an answer that is spectacularly wrong, it usually means one of two things. Either your theory is broken, or you're missing a key ingredient in your recipe. Since the mathematical tools were so successful with black holes, physicists began to wonder about the second possibility. What was the crucial difference between studying a black hole and studying the entire universe? The answer is as simple as it is profound. When we study a black hole, we do so from the outside. There is always an observer, separate from the system looking in. But for a closed universe, there is no outside. Where then is the observer? This question led to a radical and mind-bending proposal. Perhaps the complexity of the universe only appears when an observer is part of the system. Maybe the universe in its theoretical objective state, the view from nowhere, really that simple one-state entity. But the moment you introduce an observer, a physicist, a conscious being, or even just a measuring device that creates a record, the picture dramatically changes. The observer doesn't just passively witness the universe. Their very presence might be what coaxes the universe out of its simple state and into the rich, complex tapestry we experience. This is a wild departure from the traditional way of thinking in physics. Science has always strived to remove the observer from the equation. The goal was to describe reality as it would be if we weren't here to see it. We want the laws of nature, not the laws of nature as perceived by humans. But this new paradox suggests that this goal might be impossible, at least for a closed universe. The very act of describing the universe from within it fundamentally changes the description. It's like trying to take a picture of a room that includes every single thing in the room, including the camera itself, without the camera appearing in the photo. The idea that the observer plays a crucial role isn't entirely new to physics. Quantum mechanics has long flirted with this concept. The famous double-slit experiment, for instance, shows that particles like electrons behave differently when we watch them versus when we don't. But this new cosmic paradox elevates the observer from a quirky feature of small-scale quantum experiments to a central player in the structure of the entire cosmos. It suggests that without a view from somewhere, there might be nothing to see. The universe, it seems, might be a performance that requires an audience to even have a script. So, how could the mere presence of an observer conjure complexity out of simplicity? The answer might lie in the idea of creating boundaries. In late 2024 and early 2025, several teams of physicists, including one at MIT with Ying Zhao, Daniel Harlow, and Mikhailo Usatiuk, began to formalize this idea. They proposed that an observer, by their very nature, splits the universe into at least two parts: the observer and the observed. This act of division, of creating an internal boundary within the cosmos, is what breaks the perfect simplistic symmetry of the one-state universe. It's kind of like drawing a line down the middle of a blank page. Suddenly you have two regions, a left side and a right side, and the page is no longer featureless. Edgar Shagulian, a physicist at UC Santa Cruz, had proposed a similar concept in a 2023 essay, drawing an analogy from a field of math called topology. In some topological theories, a single unbroken space has a very simple mathematical description. But if you cut that space into different zones or regions, the mathematical description of the relationships between those zones becomes much more complex. Shagulian suggested that an observer does something similar to the universe. By existing, an observer and their measuring apparatus create a boundary that separates them from the rest of the cosmos, and this division is what allows for a rich tapestry of information to exist. Imagine the universe as a perfectly still, uniform pond. From a bird's eye view, it's just one thing: water. But now, dip your finger into it. You've created a boundary, the edge of your finger, and suddenly there's a whole world of complexity. There are ripples spreading outwards, interactions between the water and your skin, changes in temperature. You haven't really added anything new to the water itself, but by dividing it into finger and not finger, you've allowed for a host of new states and relationships to emerge. The observer in this view is the finger that touches the cosmic pond and brings it to life with ripples of information. The MIT team showed this with rigorous mathematics. They introduced a classical observer into their model of a closed universe. This observer, simply by being a distinct system that could make and store measurements, acted as a new internal boundary. When they recalculated the universe's information content with this boundary included, the paradox vanished. The Hilbert space was no longer one-dimensional. It became enormous, just as you'd expect for our complex cosmos. The universe wasn't simple anymore. It was now capable of holding the vast amount of information needed for stars, galaxies, and the observers themselves. The act of observation, it seems, doesn't just record the story of the universe, it helps write it. This potential resolution to the cosmic paradox carries a staggering implication. The quest for a single, objective view from nowhere description of reality may be doomed from the start. For centuries, the dream of physics, from Newton to Einstein, has been to uncover the eternal laws that govern the cosmos, independent of who or what is observing it. We've called this the God's eye view, a perspective that sees the entire cosmic machine, from the beginning to the end, in one timeless glance. But if the universe's complexity only manifests for an observer within it, then such a perspective is not just unattainable, it's meaningless. This forces us to shift from seeking a view from nowhere to accepting that the only meaningful descriptions of the universe are views from somewhere. My description of the universe is valid from my perspective. Your description is valid from yours. An alien civilization in the Andromeda galaxy would have its own valid description. Each viewpoint is defined by the boundary separating the observer from the observed. According to this idea, there is no master description that encompasses all others, because the very act of describing creates a context, a point of view that is part of the reality being described. This doesn't mean that reality is a free-for-all, where anything goes. The laws of physics are still the laws of physics. Gravity still works the same way for me as it does for an alien in another galaxy. However, the total information content of the universe, the specific arrangement of all its bits, might be a context-dependent property. Think of it like a conversation. The words being spoken are objective, but the meaning and experience of the conversation are entirely dependent on who is participating in it. An outsider might record the sounds, but they can't access the shared understanding and history that exists between the participants. This is a profound and humbling shift. It suggests that we are not, and can never be, detached spectators of the cosmic drama. We are actors on the stage, and our presence helps shape the play itself. The universe we see, in all its grandeur and detail, is the universe as seen by us. Another observer, with a different kind of consciousness or different measuring tools, might partition the universe differently, and thus perceive a different, yet equally valid: cosmic reality. The dream of a single, ultimate truth about the universe gives way to a tapestry of interconnected, subjective truths, all woven from the same fundamental laws but experienced from unique points of view. This idea of an observer-dependent reality might sound strange, but it echoes other concepts that are already well established in physics. Think about entropy, which is often described as a measure of disorder. More precisely, entropy is a measure of an observer's ignorance about a system. Imagine a room full of air molecules. If you know the exact position and velocity of every single molecule, the entropy is zero. But because we can't track them all, we describe them with statistical properties like temperature and pressure, and the system has high entropy. The entropy isn't an objective property of the air itself, it's a property of our limited knowledge of the air. This subjective nature of information was clarified back in 1957 by the physicist E.T. Jaynes and has been explored in modern experiments. It tells us that what we measure depends on the questions we can ask and the distinctions we can make. Your phone sees a world of digital signals that are invisible to your eyes. A bee sees patterns on flowers in ultraviolet light that you can't perceive. The reality of the flower is different for you and the bee because you are different observers with different boundaries and different ways of gathering information. The cosmic paradox suggests this principle might apply to the entire universe. The new proposal takes this a step further. It's not just that our knowledge is limited, it's that the universe's capacity for complexity, its very ability to contain information, might be generated by the act of partitioning it with our observations. Without a boundary to distinguish between this and that, the universe remains in a state of perfect, undifferentiated unity, which mathematically translates to that single, informationless state. The universe doesn't have a vast, pre-existing library of information that we slowly discover. Rather, our questions and measurements help to populate the shelves. This doesn't mean we create the universe out of thin air just by looking at it. The fundamental laws and the raw potential are already there, but the specific manifestation of reality, the arrangement of its matter and energy into the complex patterns we see, is something that might be realized only in the relationship between the cosmos and an observer within it. Reality, in this sense, becomes a profoundly relational concept. A thing is not just what it is in isolation, it is what it is in relation to an observer who can measure it, describe it, and distinguish it from everything else. The universe's story is a shared one. We stand at a fascinating crossroads in our understanding of the universe. The paradox born from black hole physics has forced us to confront our most basic assumptions about reality. The idea that an observer is necessary to unlock the cosmos's complexity is still a tentative proposal, and physicists are working tirelessly to test its limits and explore other possibilities. Perhaps there is a flaw in the island formula, or maybe our understanding of quantum gravity is still missing a crucial piece that will resolve the paradox without resorting to such a radical, observer-centric solution. Science is a process of constant questioning, and this is one of the biggest questions yet. But if this idea holds, it will reshape our place in the cosmos. It would mean that the age-old philosophical question, if a tree falls in a forest and no one is around to hear it, does it make a sound, has a cosmic equivalent. If a universe exists with no observer inside it, does it contain any information? The answer might be no. The universe might need a witness to come alive. This elevates the role of conscious information processing beings from a mere cosmic accident to a potentially fundamental component of reality itself. We are not just stardust. We may be the universe's way of knowing itself. This journey of discovery is far from over. Physicists will continue to probe these ideas, building more sophisticated models and searching for ways to test them. Can we formalize what counts as an observer? Does it have to be a conscious being, or is a simple measuring device enough? What does this mean for the early universe, before any life or complex structures existed? These are the questions that will occupy the next generation of scientists as they chart this new, unfamiliar territory, where the observer and the observed are inextricably linked. Ultimately, this cosmic paradox leaves us with a profound and humbling thought. For all our attempts to find a final objective truth, we may find that we are woven into the fabric of that truth. The story of the universe may not be a monologue delivered by the laws of nature, but a dialogue, a conversation between the cosmos and the minds within it. We are not just reading the book of the universe, we may be co-authoring it, our every observation adding a new sentence, our every discovery adding a new page. And the question that remains is one we can never fully step outside of to answer. What is the nature of a universe that requires a mind to behold it?